The objective of this video is to understand what is meant by a sampling distribution of a statistic. So let's recall, what is a statistic? It's a measurement describing some characteristic of a sample. So remember, these things we've learned so far are like the mean, x bar, the standard deviation of a sample, s, or we've seen the variance of a sample, s squared. We've talked about the median and the range. These are all ways we can describe a sample. And there's one we haven't really talked about yet, but we will be, and it's called the proportion. So we may talk about the proportion of females in a group or something like that, proportion. Okay, so that's what we mean by a statistic. So what is a sampling distribution of a statistic? Well, this is a table or a probability histogram or a formula that gives the distribution of all values of the statistic when all possible samples of the same size n are taken from the same population. Now that says a lot. This is some way we've put together a place we can find the values or calculate the values of a statistic when we have collected every possible sample of the same size taken from that same population. Okay, so let's look at an example of a sampling distribution of a statistic, and we'll look at the sampling distribution of the mean. That's one of our statistics. And we want to create a table. As we said, it could be a table that gives all the possible values, a distribution of all the values of the statistic of the mean when all possible samples of the same size n are taken from the population. Well, to do this, we're going to need a very, very small population for me to actually be able to come up with every possible sample of that size. So we'll look at what we'll consider a pretty ridiculous situation, but it's going to help us understand because the population size is small enough we can actually run the numbers here in an example. Okay, but it's a very, very, very small population. Okay, so Farmer Fred had 12 chickens to provide his family with eggs. He decided to keep a record of their egg production. On the first day, the chickens produced 7 eggs. On the second day, they produced 12 eggs. And on the third day, they produced 5 eggs. And on the night of the third day, a fox got in the hen house and killed all of the chickens. So we want to create a sampling distribution of the sample mean for the number of eggs produced. And see, this is our population. There were only 3 days of egg production total. So that is our entire population. So let's make note of that. See, keep our numbers handy right there. All right, so our population consists of the first day 7 eggs, the second day 12 eggs, the third day 5 eggs. That's it. That's our whole population. Okay, so the population size, capital N, is 3. All right, so we can look at that and easily calculate the population mean. So that would be mu, right? That's the Greek letter representing our population parameter. So the population mean is 5 plus 7 plus 12 divided by 3, or 24 divided by 3, or 8 eggs. Okay, so that's the population mean. Now what we want to do is list all possible samples, and we'll use a sample size of 2 drawn with replacement from the population. So that's our next step. Okay, so we'll have our samples listed here. Okay, So with replacement, so I'm drawing from my 3 different possible days of production. So on my first draw, I could get the day where they had 5 eggs were produced, and then I replace it, and I draw again, and I get that same day with replacement, right? Or I could draw the day that they got 5 eggs, and then the day they got 7. Or the day they got 5, and the day they got 12. Okay? Or I could draw 7 and then 5, 7 and then 7, 7 and then 12. These are my only choices, are these 3 numbers, the production of eggs on those 3 days. So you can see my pattern I'm using here. Then I could draw the day of 12 and the day of 5, the day of 12 and the day of 7, and the day of 12. And with replacement, I could get that same day again. So now what I want to do is compute the mean for each one of my samples. So these are sample means, x bar. Okay, well, with this first sample, of course, it's 5 plus 5 over 2, or a mean of 5. My second sample, 5 plus 7 over 2, or a mean of 6, right? 12 over 2. 5 plus 12 over 2, so I've got 17 over 2, so that comes out to 8.5. Okay, 7 and 5, I already did that one, right? I had 5, 7, 7 and 5, we said that was 6. 7 and 7, well, 7 plus 7 is 14 divided by 2 is going to be 7, right? 7 plus 12, haven't done that one, 7 plus 12 divided by 2, that's 19 over 2, and that's 9.5. 12 plus 5, well, I did 5 plus 12, that was 8.5. 12 plus 7, well, I just did 7 plus 12, 9.5. And an average for this one, of course, is 12. So these are all the possible sample means. For every possible sample I could draw of size 2 from this population, that's it. Because my population is so small, we can actually see all possible samples, all possible sample means. Well, one way then to get the average, the mean of the sample means, would be to add all these up, right? So the mean of the sample means well, I would take, what, 5 plus 6 plus 8.5 plus 6 plus 7 plus 9.5 plus 8.5 plus 9.5 plus 12, and divide that by the number of samples we had. And we had 1, 2, 3, 4, 5, 6, 7, 8, 9 samples. So I divide this by 9. Okay, when you add all those up, you get 72. And notice we get 8 eggs. That's what we had for our population mean. And now we see that the mean of all the sample means is also 8 eggs. Well, now let's create a probability distribution. That's what this is about, a probability distribution for the mean number of eggs produced. That's what we were to produce, as a probability distribution. Okay, so for each possible mean, these are all my possible sample means, and this is the probability that I might get that sample mean. Okay, and then we'll do our x times p of x here. Okay, so let's see what our means were. Well, we had a mean of 5. That's one possible sample mean. Another possible sample mean was 6, if I try to get these in numerical order. 6 was a possibility, 7 was a possible mean, and then we went to 8.5, 9.5, and 12. And that was it. Those were all the different sample means we found. Now, what's the probability that we get 5 as a sample mean? Well, how many ways were there to get 5 as a sample mean? Just one. Here it is, right here. One way to get 5 out of how many possible sample means did we have? Well, we had 9. So, change the color here. So the probability of getting 5 as a sample mean is 1/9. Alright, how about 6? How many ways can we get 6? Well, here's one, and here's one. So the ways to get 6 are 2/9. Or the probability of getting a 6, sorry. 2 out of 9 possible ways. How about 7? Let's see, change my color. To get a 7, there it is, just one way. So that's 1/9 for 7. 8.5. Where's 8.5? So let's see, I'll use an arrow this time. There's an 8.5. There's an 8.5. Is that it? 2 ways to get 8.5 out of 9 possible ways to get a sample mean. 9.5. Okay, let's see, 9.5. There's a 9.5. Here's a 9.5. That's it. 2 ways to get 9.5. And then how about our 12? Here it is. I'll put a box around it. There's just one. One way out of 9 possible sample means ends up being a 12. And then we check. This should sum to 1, right? So 1 plus 2 is 3, plus 1 is 4, plus 2 is 6, plus 2 is 8, plus 1 is 9. So good. We've accounted for our entire values of our probabilities, our entire sample space, right? That's it. That's all the possible sample means. Now we'll multiply across. Okay, so 5 times 1/9 is 5/9. And 6 times 2/9 is 12/9. I'm not going to reduce any of these fractions. I'm going to keep a common denominator. 7 times 1/9 is 7/9. 8.5 times 2/9 is 17/9. 9.5 times 2/9 is 19/9. And 12 times 1/9 is 12/9. And so now we do our sum of the x times p of x. That's the sum of this column, right? We've done this before to get the mean. And that's 72/9, or 8. Okay, so this is a mean. This is our mean of our sample means here. So again, we found the mean of the sample means. We found it a different way using our probability distribution. So the mean of a sampling distribution, of this sampling distribution, is 8, which is also equal to the mean of the population. Remember when we found the mean of the population? Way back here, we defined our population here in yellow, and we found the population mean. 5 plus 7 plus 12 divided by 3, 8. And we've shown the mean of the sample means to be exactly the same. Well, these results are true for any population size. These results, in other words, population or mean of sample means, let me say it that way, mean of sample means is equal to population mean. These results are true for any population size, any capital N. That's really important. Okay, so why that's important is because we can't possibly look at a real population, come up with every possible sample of the same size, and run through this calculation. Most of our populations are very large, certainly larger than 3. But if we can demonstrate this with a teeny little population, then we can understand it's true for any size n. Okay, so in summary, what are we saying? We're looking at 2 important properties of the sampling distribution of the mean. First one is that the sample means target the value of the population mean. What we mean by that is that as we get all of the sample means, they end up actually being equal to the population mean. So we know that the mean of the sample means is the population mean. Let me make a note of that. Okay, and likewise we can say the expected value of the sample mean is the population mean, because those are the same thing. So let's just remember that. The expected value of the sample mean is the population mean. So we say that the mean is an unbiased estimator. This is an important distinction. Unbiased estimator. In other words, the sample mean is an unbiased estimator of the population mean. Very important. Okay, and finally our second property, the distribution of the sample means tends to be a normal distribution as the sample size increases. Okay, as we get larger samples, the distribution of the sample means tends to be a normal distribution. That's a property of the sampling distribution of the sample mean. So that was an example of using the mean as our statistic. Your textbook and in your homework you'll see other statistics that have sampling distributions created for them.